Hi everyone. In today's video, I will figure out the noise figure of this commercial LNB. In my last video, I tried out a few of these and I came to the conclusion that this one was the best. It was a bit better than the other one I tried out. Um, but the way I tested it was just to receive the Oscar 100 satellite and see how good signal to noise ratio was, which is, that's a fair test, I guess. But sometimes you want to have a number on these, how good they are. And today I'll show you how you can calculate the noise figure without using any kind of measurement instruments. You only need this LNB and a receiver so that you can receive the output from it. And it's a pretty neat trick, and I think you'll like it. And so let's go outside and see how you do that. So this is the SDR console running. There's the LNB. Back here we have my stabilization unit that also feeds power to the LNB. Small battery pack powers this, and an SDR. So this down converts from 10 gigahertz down to between 200 and 800 megahertz. So right now I'm running on an I frequency of 750 megahertz. That corresponds to the receiver receiving on 10.5 gig. So what we see here is the noise level. There's nothing running here, so just the noise from the sky up there. But watch what happens when I point that in another direction. There's an interesting phenomenon. So let's just put it over here so you can see it in one shot. So if you see the noise level here, watch what happens now when I tilt it. See, the noise level goes up a fair bit and back and goes down again. So what's happening here is looking to the cold sky here, and now it's looking to the warm earth or the bushes over there, but it doesn't matter. Anything that is warm. So it could actually be my hand or anything. So you can easily see it here. If I put my hand there, the heat from my hand is enough to bring up the noise level. So if you compare these two levels, you can calculate the performance of this. You can calculate the noise figure of it. So I did that today. And I'll just go over briefly how I did this. I used the SDR sharp, and as it is running now, you can put the cursor and you can see the noise floor. So there you see the noise floor is now 104.6, and now if I tilt it, get a second value, you see it's now 100.8. So you can plug that into a calculator and you can find out what the noise figure is. So what you do is you put in the difference between the cold sky, the noise there, and the hot earth. So if we go back to SDS sharp again, I can show you how I did that. So what you have to do is you have to lower the speed of. So there's a setting here called smoothing. Sorry for the camera work. But what you do is you drag these sliders to, as you see that when you drive them to the left side, you get a bit of an averaging, so it's easier to read the value. So let's do that. Let's see what kind of value we have. So I'm now pointing towards the sky. Let's say it's 104 point. 7, 104.8. And now I will tilt it. And then you use a calculator. So 104.0 was the sky value, and now we have, if you look here at floor, 100.5. So subtract that, 100.5. So 4.3 decibel is the difference between the sky noise and the ground noise. And you plug that into the spreadsheet, and so you do it here at the results. 4.3. You also enter the earth temperature, the daily temperature. So it's 296 today, that's 23 Celsius. And you can also plug in different value here, but just I'll just kept it as it was here, and you get the system noise figure here. So about 1.5, 1.6 decibel is the noise figure of this, and that was on the frequency we just measured, which was 10.5 gigahertz. And so what I've done is I've done that for lots of different frequencies. Started at 10.5 and then going 100 hertz down. So I got this value. So this is pretty much the same value across the bands. There's a slight variation, as you see, but so it's about 1.5 is the noise figure, regardless of what kind of frequency. Okay, we are back inside again. It's evening, and we had a good day outdoors. Trying out this pretty unique measurements without using any instruments, just the receiver. I think it's pretty neat. So the noise figure came out to be 1.5, which is probably, fairly correct. I would have guessed without any prior knowledge that they're probably around 1 decibel. And there was some variation. I tested on several frequencies there. There was some frequency that was a bit lower, maybe down to 1.1, something like that. So the spreadsheet will be linked in the description. That's what you use to plug in your values. The difference between the hot earth and the cold sky, that's called a Y value. So this is a Y value measurements. Should be accurate. I suggest you try it out and see what you can come up with if your measurements match mine. I know that a lot of engineers have been using this technique for a long time, and they still do. Instead of measuring the earth and the sky, you can measure the sun noise. You can even measure the moon noise. So I know that they use these kind of techniques, and but I thought this was so easy to do. Just use like these two, sky and ground. So easy, anyone can do it. So that's what I wanted to try it out. On the next video, we'll do a proper measurement using my noise figure instrument, and we'll see if that matches up with this with this measurement. So we'll see if 1.5 as a noise figure, if that is what the instrument will come up with. Okay, so anyway, I'll hope you enjoyed this, and I suggest you try it out if you have a receiver, a microwave receiver that you want to see if you can measure. All right, thank you, and see you in the next one.